Hi guys, I hope you are doing well and preparing for your exam. Now you guys are on your preparatory leave, so we are unable to connect. But yeah, some of you are coming to school to ask me doubts. So what I thought is to create a video for you. And the today's topic is magnetic effect of electric current. And this topic is important from your MYP 5 exam point of view. And in this topic, what we are going to discuss first is the magnetic field around a conductor. So we have already discussed this topic in the class, but again for revision purpose we are doing it. So I will start it from the beginning. So imagine this pen is acting as a conductor, and the top of the pin is pointing in the direction of current. So this is a conductor, and this conductor is carrying current in upward direction, something like this. Now as current flows in this wire, then what we observe is the magnetic fields are generated around this conductor, and at each and every part of the wire there is magnetic field generated. So if you take this part, there is also magnetic field, this part magnetic field, this part magnetic field. It means I can say at each and every point of the wire there is magnetic field generated around it. And these magnetic field lines, they are in the form of circle, something like this. Now as you move away from the wire, this circle increases in its radius, and the distance between the two circles also keep on increasing. And increasing distance between the two circles represents that the magnetic field becomes weak. Magnetic field is weak. And the point where magnetic field lines are closer or the circles are closer, it represents strong magnetic field. So what you can see here, you can see here a current carrying conductor, and this current carrying conductor is generating magnetic field around itself. Now the question is, if there are magnetic field lines, there must be direction of magnetic field lines. So how do we know what is the direction of magnetic field lines? So this is the question, direction of magnetic field. So to find the direction of magnetic field, we use right hand thumb rule. So again I can take this pen, and this pen, if I'm holding it in my right hand, and the current which is flowing in this conductor is pointing in the direction of my thumb. So this is the conductor, direction of current is upward, and my thumb is also pointing upward. So if I'm holding this conductor in my hand, something like this, so when the thumb points in the direction of current, then my curled fingers, you can see this, right? The curled fingers they will point in the direction of magnetic field lines. So this is a very easier way to find the direction of magnetic field by using the right hand thumb rule. So when this wire is carrying current upward, then magnetic field lines will go something like this. It means from the right side of the wire they will go backward, and from the left side of wire they will come forward. So now if I draw the wire again in this vertical plane, so the magnetic field around the wire is circular, and the direction of magnetic field to the left and to the right of the wire will look something like this. To the left of the wire, it will come out, and when the magnetic field lines or electric field lines or the current is coming out, we represent it by dot. And when the magnetic field lines are going into the page, we represent them by cross. So you know, at the right side of this wire, magnetic field lines are going into the page. So we can easily find the direction of the magnetic field. Now let me change the direction of flow of current in this wire. So if now wire is kept horizontal, imagine, and the current is flowing towards the right side. So horizontal wire and current is flowing towards the right side. What would be the direction of magnetic field around this wire? So if I apply the right hand thumb rule, imagine this marker is pointing in the direction of current, something like this. Then if I hold this marker in my right hand and my thumb is pointing in the direction of the current, then magnetic field lines will be in the direction of my curled fingers. So what you can see, if you see the lower part of my hand, this part, it's going towards this whiteboard, and the upper part of the hand, it means this fingers, they are coming towards the camera. It means they are coming towards you. So the upper part, this part is pointing towards you. It means we will represent the magnetic field lines by dot. And the lower part of the wire, or we can say the region which is below the wire, it's pointing the magnetic field lines into the page or into the board. Then we will draw it by cross. So this is how we represent the magnetic field lines around a conductor when that conductor is carrying current. Now if you bend this wire in the form of loop, then what we can get is the direction of magnetic field for each and every part of wire will behave differently. And let me draw that. So magnetic field due to loop. So what I'm doing is I'm taking a simple loop. Imagine this circular loop, and these are the two ends carrying current in this loop. So the current from left end enters into this loop, and it's going something like this and coming out of the loop. So the direction of current here is something like this. Now to find the direction of magnetic field within this loop and the outside of the loop, what you can use is the right hand thumb rule. But sometimes because this is bent, you do not want to use right hand thumb rule, then you can use a simple rule. And that is called as clock rule. And what is that clock rule? Let me explain it to you. So imagine this current is flowing clockwise. And yeah, as I have represented here, the current is flowing clockwise. When the current is flowing clockwise, then the part of this loop which is your side, this part. So if I'm taking this wire cable as a loop, then this part is towards you and the back side of this loop is towards me, right? My side. So if the current is flowing clockwise, then the part which is towards you will behave as, let me draw it here. See, the ends of this letter S, they are pointing in the direction of current. So if the current is flowing clockwise, then the part which is towards you will act as south pole, and the part which is towards me, it means just back side of the loop, will act as north pole. And on this board, the part which is back side of this south pole will act as north pole. So इसका मतलब क्या हुआ? अब मैं हिंदी में बोल रहा हूं. इसका मतलब ये हुआ कि जो आपको क्लॉकवाइज दिख रहा है वो मुझे एक्चुअली एंटी क्लॉकवाइज दिखेगा, राइट? It means if the current is flowing anti-clockwise, something like this. Imagine this is the new loop in which the current is flowing anti-clockwise. If the current is flowing anti-clockwise, then the part of the loop which is towards you, earlier it was towards me, so it was looking to me like anti-clockwise, and it was north pole for me. Now if you are facing this loop and in that loop current is flowing in anti-clockwise direction, then this side will act as north pole, right? Now there is one challenge. If this is acting as north pole, then how we will draw the magnetic field lines within this loop and the magnetic field lines within this loop? So here you saw that when the magnetic field lines are coming towards you, then you represent them by dot, and if the magnetic field lines are going away from you, you represent them by cross. Why do you do so? The reason is we take this idea from the arrow, and let me explain you that. So imagine there is an arrow something like this, and here is an observer who's standing and observing the motion of the arrow. If the arrow is going forward, then what the observer will see? Observer will see the head, and the head is pointed, so it will look like a dot, right? But if observer is here and arrow is moving forward, because of this feather, the arrow will look like cross. So when the magnetic field lines are going away from us, we represent them by cross, and if they are coming towards us, we represent them by dot, right? So same idea we can use, but I have to rub this because I need some space. So imagine these are the two circles now, and one circle is carrying current in clockwise direction and another one is carrying current in anti-clockwise direction. Then you know this circle which is carrying current in clockwise direction will act as south pole, and the one which is carrying current in anti-clockwise direction will act as north pole, right? Provided we are facing those sides. So in this case, when the current is clockwise, it's acting as a south pole, and in case of south pole, we know the magnetic field lines go into the pole. If you don't believe or if you don't remember, then just draw the bar magnet north and south pole, and the magnetic field lines are coming out from the north pole and magnetic field lines are entering into the south pole. So in case of clockwise, this is acting as south pole, so the magnetic field lines will go into the board or go into the page when you are writing. And in case of anti-clockwise, this is acting as north pole, so the magnetic field lines, they will come out of this loop. So magnetic field lines are coming out. Now, if you take n number of loops and you stack them one after the another on a cylinder or a pipe, plastic pipe, or you can take a paper pipe and you can take a copper wire and you can wrap that wire. So what you will get is you will get a solenoid. And solenoid looks something like this. And when current flows in this solenoid, and let me write the name of the topic, solenoid. So when current flows into this solenoid, it starts acting as a weak bar magnet. How to make it strong bar magnet? I will tell you. That is called as electromagnet. But now imagine there is a hollow cylinder and this copper wire is carrying current, and there are large number of loops. You will call it solenoid, right? And this solenoid will also generate magnetic field, and you can draw the magnetic field lines something like this. I will not draw the direction because we are not sure about the direction of current. We will discuss that as well. What would be the direction of the current, then what would be the direction of pole, but later on. So this is acting as a solenoid, and a solenoid is very much like a bar magnet. Now let's go to the other topic, and the name of that topic is force acting on a wire kept in magnetic field. So imagine there is a wire, something like this, and it's kept between the two poles of the magnet. This is north pole, this is south pole. Name of the topic is force acting on a wire in magnetic field, and this wire is carrying current. I'm not writing that because it's too long. So force acting on a wire carrying current which is kept in magnetic field. What happens? Magnetic field lines from north pole, they will come towards the south pole, and this wire which is in between the two poles is very much in the magnetic field. And when this wire is in magnetic field and the current I flows in this wire, then this wire experiences force. And the force experienced by the wire into the magnetic field, IBL. So F is equal to IBL. Here I is current which is flowing in the wire. and B is the magnetic field strength, magnetic field strength, and L is the length of the wire, not the total length of the wire, the length of the wire which is in